Okay, after the Taylor series for the exponential function, we're going to look at other Taylor series for well-known functions. So, for example, have a look at fx equals the sine of x, and we're going to look at the Taylor approximations in a equals the Taylor polynomials in a equals 0. Well, recall that we already deduced that the odd Taylor polynomials of odd order can be expressed as such, right? So k equals 0 to n minus 1 to the power k times x to the power 2k plus 1 divided by 2k plus 1 factorial, right? Um, and this, of course, equals the Taylor polynomial with the even index as the um, the 2n plus 2th derivative of the function equals 0, right? So we have this result here. Okay, but then we have, look at the remainder term in absolute value. We use Taylor here, so we can express the remainder term in terms of the higher order derivative in some psi of x in between 0 and x. I'm going to divide it by 2n plus 2 factorial times x to the power 2n plus 2 plus 2 should be not 1. Then we get that this one is smaller equal, well, the derivatives of f are all sines, all versions of sines and cosines. But we know that the sine and cosines in absolute value are always smaller equal than 1, right? So what we can do now is showing that this is smaller than equal than 1 in absolute value, so we get this one, right? So we get that this term here is smaller equal than 2n plus 2 x to the power 2n plus 2 divided by 2n plus 2 factorial, right? So we've already seen that for a fixed x, this limit goes to 0 when n goes to infinity, right? In the same fashion, we can just show that the remainder term um, for the remainder term for the 2n plus 2th Taylor polynomial approximation depends on the 2n plus 3 derivative of x in such a way so that we get, for the same reason, these derivatives here are all smaller or equal than 1 in absolute terms. So we get that this is smaller or equal than x to the power 2n plus 3. There's a small mistake here. There should be a 3 here and also a 3 here, so that we get that this also goes to 0 when n goes to infinity, right? So as a conclusion, what we have is that the remainder term for a fixed value of x always vanishes when n is taken large enough. So we know that fx equals its Taylor series, and the Taylor series of the sine equals x minus x to the power 3 divided by 3 a factorial, etc., etc. Yeah, and something similar we get for the cosine, right? You might try it yourself. Okay, the next example is an interesting one. So here we look at fx equals 1 divided by 1 minus x. And we're going to look at Taylor approximations in 0. Well, notice that the domain of f equals r except for 1, right? So we can only not put 1 here in the numerator, since then the numerator would become 0, and that's not possible, right? So now let's take derivatives. So if we take the first order derivative, we get a minus for this 1 minus x, and we get a minus 1 for dividing by 1 minus x, so we get 1 over 1 minus x squared, and in this way we continue. So f double prime of x equals 2 divided by 1 minus x to the power 3, and in the same fashion we see that the kth derivative of this function is k factorial divided 1 minus x divided by k plus 1, right? And so we have, in particular, if we plug in the value 0, because we're going to look at Taylor polynomials in 0, then we need those derivatives in 0. We see that if we plug in 0, then we see here that we get 1 to the power k plus 1, which is just 1. So we get k factorial. Yeah. So the nth order Taylor polynomial, which is defined as f0 plus f prime 0 times x plus etc., plus the nth order derivative in 0 divided by n factorial times x to the power n, then equals 1 plus x squared, etc., right? Plus x to the power n, right? Hey, but this is something we've seen before, right? So we know that basically for x smaller in absolute value than 1, that 1 over 1 minus x equals a geometric series, right? So we have that the limit of n to infinity of Tn of x exists only if x is in between minus 1 and 1. Yeah, so we have a convergence radius of 1, right? So we also have that fx equals its Taylor series only on this interval, right? Only for x in between minus 1 and 1. Yeah, and then notice that the domain of f is way larger, right? So it doesn't mean that the Taylor series of a function is always equal to a function. Okay, the final example here in this clip is the function fx is the ln of 1 plus x. We look at the Taylor series at a equals 0. Notice that the domain of this function is minus 1 infinity. Okay, in order to determine the Taylor polynomials in 0, we need a lot of derivatives, right? So the first order derivative is 1 divided by 1 plus x. The second order derivative equals minus 1 divided by 1 plus x to the power 2, etc., right? So the third order derivative equals minus 2 times minus 1, so that will be 2 factorial divided by 1 plus x. Fk, the kth derivative in x, equals minus 1 to the power k plus 1 times k minus 1 factorial, and we're going to divide it by 1 plus x to the power k, right? So we see that if we plug in the 0 here for the derivative, the 0 derivative then equals minus 1 to the power k plus 1 times k minus 1 factorial, right? And this holds for k equals 1, etc. Okay, now have a look at the nth Taylor polynomial, nth order Taylor polynomial at 0. So we just calculate this term here. We just plug in what we just found, then we get the sum of k equals 1, right? So we don't have, since we have that the f of 0 is 0, then we start counting with k equals 1. So this makes minus 1 to k plus 1 times k minus 1 factorial divided by k factorial times x to the power k. So we see that here there's something cancelling, right? So we only get k here, so that we see that this is just the sum of k equals 1 to n of minus 1 to the k plus 1 divided by k xk, right? So we have, as a Taylor series, we have this one, right? Just rewrite it now with an infinite sum, right? So the Taylor polynomial equals x minus x squared divided by 2 plus x to the power 3 divided by 3, etc., etc., right? Okay. Well, in the past, we already have looked at the interval of convergence, but we'll repeat it here, right? So the ratio test, if we just look at the n plus 1th element in this sequence divided by the nth element from these elements, then we get minus 1 to the n plus minus 1 to the n plus 2 divided by n plus 1 times n plus 1, right, divided by minus 1 to the n plus 1 divided by n times x to the power n. And now a lot of terms cancel, right? So we the signs move out because we take absolute values. So the minus 1 to the powers, they move out. And then we simplify the expression, right? So the expression now gets n divided by n plus 1 times the absolute value times x, right? And this is converging to x for n to infinity, right? So we see that this series only converges for x in absolute value smaller than 1, right? So we get a ratio of convergence, radius of convergence, equal to 1 for this series. So what do we get as an interval of convergence? Well, the interval of convergence for this one is, well, we know that the series converges for x in absolute value smaller than 1. So there we're okay, right? But we should check two other points. X equals 1, right? So if we look at t infinity 1, that would be the series k equals 1, the sum of k equals 1 to infinity of minus 1 to the k plus 1 divided by k. Yeah, and this is convergent as an alternating series, right? So we've shown this in the past. So 1 over k is monotonically decreasing with limit 0. So this is a convergent alternating series. If we look at x equals minus 1, then t infinity minus 1 is the sum of k equals 1 of minus 1 to the k to the 2k plus 1 divided by k. Yeah, but that goes wrong, right? So this is equal to minus the sum over 1 over k, which is divergent, right? So this is the harmonic sequence, harmonic series, which has as a limit minus infinity. So the conclusion here is that t infinity x exists for x equal minus 1 and 1, right? But central question is, this is the Taylor series corresponding to f, and is f equal to its Taylor series, right? So that's the question. So to see if we can make a statement about whether or not fx equals its Taylor series, we are going to look at the remainder term, right? So if the remainder term only goes to 0, then we know that f equals its Taylor series, right? Okay, so we know by virtue of Taylor's theorem that we have the following identity for some psi of x in between x and 0, right? So we are looking at Taylor approximations in 0, and if we take x unequal to 0, then we find an psi of x such that this expression holds, right? Okay, but we also found we can also easily calculate the n plus 1 derivatives, right? So the n plus 1 derivatives are very easily found. So we have n factorial divided by 1 plus psi of x to the power n plus 1. Yeah, this is just the n plus 1th order derivative of the function we are considering, right? And we have to multiply it by x n plus 1 and divide it by n plus 1 factorial, right? So we get, as a result, what we obtain is that we get x divided by 1 plus psi x to the power n plus 1 times 1 over n, right? So if x is just positive or non-negative, for x in between 0 and 1, we have that x divided by 1 plus psi of x is smaller than 1, and hence we see that the remainder term goes to 0 for n to infinity. Okay, but for x smaller than 0, it's not at all clear, right? So it's not clear whether or not x divided by 1 plus psi of x is smaller than 1, right? But we may show, using a different technique by integration of some other power series, some other Taylor series, that indeed we always have the identity, the log of n plus x equals x minus x divided by 2 plus x to the power 3 divided by 3, etc. on the complete interval left open minus 1, right closed 1, so that also we have that the ln of 2 is 1 minus a half plus 1/3 minus 1/4 plus 1/5. Yeah, recall this one? We have been looking at the right-hand series, but now we indeed may show by just plugging into a 1 over here that we have this identity over here on the right.